All right, everybody, so let's start with how to solve part 8. So it says a hydrocarbon burns completely, producing 7.2 grams of water and 7.2 liters of carbon dioxide at standard conditions. What is the empirical formula for the hydrocarbon? So the goal here is to find an empirical formula. So an empirical formula, once again, is the simplest whole number ratio of a substance. Now, the other key component of this that we're dealing with just a hydrocarbon. So that means we're looking for a formula of C something, H something. So when you're looking for subscripts in an empirical formula, the first thing we have to do, or the thing you always have to do, is we have to find the moles of just carbon and just hydrogen. So since they gave us amounts of water and carbon dioxide, the first step is we need to isolate the carbon and the hydrogen from those two things. So here's how we'll set it up. So we'll take our 7.2 grams of H2O, and the first step is I'm going to convert that into moles. So there are 18.02 grams in 1 mole of H2O, because that's its molar mass. And then in every 1 mole of water, there are 2 moles of hydrogen, because that little 2 right there. Okay, similar setup for our carbon dioxide. So this one says we have 7.2 liters of CO2. Now I need to get to moles as well, which is where this relationship comes into play. Because at standard conditions, there are 22.4 liters per every mole of a gas. So then for 1 mole of CO2, we just have 1 mole of carbon. Okay, so we plug those into our calculators and we get here, I got 0.80 moles of H and 0.32 moles of C. Okay, next step is you take whichever is the smaller of the two and divide by that. So we're going to divide them both by 0.32. This one ends up giving you about 2.5, and this one ends up being 1. Now, at this point, once you divide by the smallest, if it's not a whole number, then we have to multiply by something to get it to a whole number. So since it's 2.5, this one would get times by 2. They both get times by 2. So we get 5 and 1. So our final answer, 5 and 2, sorry. So our final answer would be C2H5. Okay, for part B, it says calculate the mass in grams of O2 required for the complete combustion of the sample of the hydrocarbon described in A. So what it's asking here is we want to know when our hydrocarbon, which has an empirical of C2H5, once again, keep in mind this is not what it truly is, or we don't know that yet, when it went through the combustion, how much O2 reacted. So we're going to do actually something fairly similar to what we did in part A, but instead of isolating the hydrogen and the carbon, we're now going to isolate just the oxygen. So, once again, starting out, we have 7.2 grams of H2O. And this time we're going to convert it into how much oxygen there is. So in 1 mole of H2O, in 1 mole of H2O, we have 1 mole of oxygen. And then since our final answer is going to be in grams, I'm just going to keep going. So 1 mole of oxygen is 16.00 grams. Okay. All right, same setup for carbon dioxide. We're going to isolate that oxygen again. So in 22, there's 22.4 liters in every mole of carbon dioxide. In 1 mole of carbon dioxide, we have 2 moles of oxygen, and then 1 mole of oxygen, 16.00 grams. Okay, we'll plug that into our calculator. All right, so after plugging it into the calculator, you get 6.39, 10.29 for the amount of oxygen in each. So then we combine those together to get the grand total of 16.67. Now, technically for sig figs, if you're thinking about that, it would actually just be 17 grams of oxygen. And there's our answer. Okay, so for part C, we're now looking for the molecular formula, which is the true formula of our empirical. So to find the molecular, you always have to have the molecular mass, which they gave us as 56.2. So what we're going to do is we're going to take the molecular mass, 56.2, and divide it by the empirical formula's mass of C2H5. Because an empirical formula, once again, is just a smaller ratio of the molecular formula. So what we're trying to figure out here is, okay, is it a multiple of 2, multiple of 3, so on and so forth. All right, so when I add up the mass, I get about 29.07. So this is what I get when I added up C2H5. So 2 carbons, 5 oxygens. Okay, so if I divide that out, we end up with pretty close to 2. If you plug it into your calculator, you get 1.93. Now, this should always be really close to a whole number because we're looking for a whole number multiple. If it's far off of a whole number, then that probably means something's wrong with your empirical. But this is close enough for 2, so that means our molecular formula would be C4H10. Because if we times all this by 2, we get our molecular formula. All right, question number 2. Part A, write a balanced equation for this reaction, excuse me, and label the type of the reaction that is taking place. So it tells us we have mercury and bromine will react, so that we have those two things together. So mercury is Hg, bromine is Br, and it is diatomic, so we need a little 2 there because it does not exist as just Br ever. Okay, will react with each other to produce, so there's my arrow, mercury to bromide. Now, I know this is an ionic compound because it's a metal and a non-metal. And so the thing I have to look at is the balancing of their charges. The Roman numeral is telling me the charge of mercury. So mercury has a +2 charge. Bromine has a -1 charge. So when they bond together, we get HgBr2. And as it is already balanced. So we don't need to add any coefficients. And this is defined as a synthesis reaction, because synthesis is when you have 2 things becoming a single product. All right, part B. What mass in grams of mercury to bromide can be produced from the reaction? So our goal is to find the amount of mercury bromide if I have 10 grams of mercury and 9 grams of bromine. Once again, don't be afraid to mark up the question, circle, underline, to help you break down what you need to do. So whenever you're trying to find an end goal and you're given 2 starting amounts, that's a signal to your brain that you need to figure out which one is limiting, because we need to know which one we're going to run out of first. So in order to know which one is limiting, you have to compare them by their moles, not by the grams. So I'm going to take my 10 grams of mercury and my 9 grams of bromine. Once again, keep in mind that it's diatomic, and convert them into moles. Okay, so for mercury has a molar mass of 200 point. Let me look at my periodic table. .59 for every 1 mole of mercury. Now you have 2 options here. To find the limiting, we just need to know which one's going to run out first. So you can just go to moles and then we can compare them because it is a 1-to-1 ratio. Or you could go all the way to product for both, and then whichever one produces the least amount is your end answer, because the other one's going to run out before you can actually make that much. It's up to you. Whatever you feel more confident with, you can do. So bromine has a molar mass of 79.9. It's diatomic, so we're going to times that by 2. So we get 159.8 for every 1 mole of Br2. Now, if you're going to just the mole step like I'm doing, you just have to be careful. If it's not a 1-to-1 ratio, then you have to also take that into account. You can't just assume that the smaller one is the one that we want. Okay, so since it is a 1-to-1 ratio and we only have this many moles of mercury, that's my limiting reactant, and so this is the one I'm going to continue with. Okay, so for every 1 mole of mercury that reacts, 1 mole of mercury 2 bromide is produced because it's a 1-to-1 in the balanced equation. And then for every 1 mole of mercury bromide, it has a mass of 360.39 grams. So then we plug that through. And we'll get an answer of something. All right, so once we plug that into our calculator, we get 17.96 grams. Now, once again, you could have done the whole process with BR2 instead of stopping at moles to compare and just gone all the way to product. I believe if you did that, you get about 20 point something. But since that is bigger than 17.96, this one is not your theoretical yield because we'll run out of mercury before we can actually make 20. Now I'm solving part C. Because it's a synthesis problem, there's a simple way to do it, and then I'll show you a way to do it in case it wasn't a synthesis. But because it's a synthesis, we know that the total mass that we used in the beginning was 19. Because I put in 10 mercury, 9 bromine, and that's all there was. I also know from part B that we made 17.96 grams of product. And since it's the synthesis, whatever didn't turn into product has to be my excess. So what we do is we just take the 19 minus the 17.96 away, and we get, what, 1.04 grams of BR2 in excess. All right, part D says, calculate the percent yield for when the experiment was done in the lab and it produced 17.1 grams of mercury 2 bromide. So the number that is achieved in the lab is always your actual yield. Once again, that has to be given in the problem, or we have to go in the lab and find it because you never know what will actually happen until you do it. So percent yield is a comparison of actual over theoretical. And then times by 100. So for our problem, we're going to take our 17.10 over our theoretical, which are 17.96, and times it by 100. Now this is a great example of a problem where, let's say you knew you needed to use this equation, but for whatever reason you couldn't find, or you didn't find, the theoretical from up above. What you could do in this problem is you could assume a theoretical. Now, it's always a good idea if you're going to assume a theoretical, try to make it a logical one. So in case of percent yield, pick something that is bigger than 17.0. It's kind of illogical to have a theoretical yield it is illogical for it to be smaller than what your actual is, because then you'll get an over 100% yield. All right, number 3. In terms of atomic structure, explain why the atomic radius of K is larger than that of Na. So first off, if you look at the periodic table in the relation to these two things, they are in the same family. So we're comparing up and down. No matter what trend you're looking at, atomic radius, ionization, electronegativity, whatever, whenever you're comparing up and down, main reason for all the differences in values is because when you go down a row on a periodic table, you add a new ring or a new energy level. And that new energy level plays a big role in, particularly with this question, the size. So the correct answer is K is larger than NA because K has one more energy level or one more shell than NA does. It's incorrect to actually say that NA has higher Zeph, because that's actually false. K has a greater Zeph. Its nucleus is stronger, but because it has 4 rows of electrons versus NA's only 3, it causes it to be that much bigger. So for part A, your answer should have one of these 2 explanations. Obviously not word for word, but the same logic. That either the valence electrons of K are in a higher energy shell than that of Na, so that obviously makes it larger, or the valence electrons of K are less attracted to its nucleus than those of Na, which thus makes its radius larger. For part B, explain why the first ionization energy of K is less than Ca. So now we're looking in the same period. So up and down, it's always about energy levels. Left to right, it's always about Zeph, or that force of the nucleus pulling on the outside electrons. So since K has 1 less proton than calcium does, but they are fairly similar in size, K is going to have a lower first ionization energy than Ca because of that less pull that it has on its valence electrons. So your answer could have something along the lines of the electron removed from K is less strongly attracted to and thus more easily removed from the K nucleus because it has fewer protons than Ca, or you could say it has less Zeph than Ca does. Part C, it says K forms a compound K2O, which is an ionic compound that is brittle. Identify another element M that is likely to form a brittle ionic compound with the formula M2O. Justify your answer in terms of the periodic table. So this question has 2 points. You need to pick another element and then justify why you picked that element. Now, because we're looking for the same pattern of bonding, K2O, M2O, that means you need to pick another element that is in K's family. So you could have picked any of them. So any Li, Na, Rb, Cs, or even Fr. Any of those would have been acceptable choices of another element. Now the justification goes to the fact of, 1, that because these are in the same family, column or group, whatever you want to call it, as K, they will have similar properties. Or you could also go off the lines of, since these all have 1 valence electron, just like K does, it will have similar types of bonding. So your justification either needs to talk about how families are related by property or that it has the same number of valence electrons.